Hello everyone, I'm Haonan from Super Scientific Software Lab, China University of Petroleum, Beijing, and my top name is TileSpMSpV, a tiled algorithm for sparse matrix sparse vector multiplication on GPUs. Cooperate with Huimin, Shibo, Zhou, Professor Tan, and Professor Liu. I will report in following 5 parts. Part 1 Introduction. Sparse matrix sparse vector multiplication, called SPMSPV for short, is an operation which multiplies a sparse matrix A with a sparse vector X and obtain a resulting sparse vector Y. SPMSPV is widely used in graph framework processing, graph algorithm acceleration, and machine learning. The calculation of SPMSPV is generally divided into 2 methods: row-wise SPMSPV and column-wise SPMSPV. There is an example of row-wise SPMSPV. It obtains the result by taking a dot product of each sparse rows of the matrix with the vector. It is usually used for SPMV calculations. There is an example of column-wise SPMSPV. It finds the corresponding column in the matrix A for each non-zero element in the vector. Multiply the non-zero elements in the column by the value in the vector x and combines the results into the resulting vector y. This way of computing makes it while all matrix elements accessed. It works well when the vectors are sparse. SPMSPV is often used in BFS acceleration. BFS is one of the most basic traversal algorithms in graph computing. The algorithm starts from a source vertex in the graph and access all reachable vertices. Each level traversal can be implemented by a SPMSPV operation. And in the figure, the graph G is represented as a matrix A, and the set of the active vertices as represented as the input vector x. After A and X perform a SPMSPV operation, the result Y is active vertices site for the next traversal. When all the non-zero elements of the result Y have been accessed, the BFS algorithm is complete. The SPMSPV operation is one of the basic BLAS operations. However, exciting work, whether using SASE or SASR, largely ignore the exploiting local sparsity in the input sparse matrix and vector. They focus on whether row or column-wise vector merging. Second, it is known that no one matrix storage formulation works for any sparsity structure. So we propose the TileSpMSpV matrix and vector format for better load balancing. Part 2 SPMSPV. First, we store sparse matrices and vectors in tiled format. The tiled method divides the input sparse matrix into several sparse matrix tiles of size nt by nt, and stores each non-zero matrix tile in different storage formats. NT can be 16, 32, or 64 in the implementation. The tiled method also stores the vector in tiles. For a vector of ln n, it will be divided into n divided by nt vector tiles. And only non-empty vector tiles will be stored. We use XPTR to record the index of the vector tile. If this is a non-empty tile, record its index position, and otherwise mark the corresponding position as -1. We use S-tile to store the non-zero element of the non-empty vector tile, and the actual location pointed to by XPTR. This method enables access to sparse vector in O1 time complexity. Then we can do SPMSPV. First, load the corresponding matrix tile data into GPU shared memory, and then find the location X tile ID where the corresponding vector tile is actually stored, according to the column position of the tile. If the X tile ID is equal to -1, it means that the vector tile has no non-zero elements, and the corresponding matrix tile doesn't need to calculate. Otherwise, get the true vector non-zero element. Finally, according to different formats of the matrix tile, different ways of multiplication can be performed. Next, I will give 2 examples. The first row tile of the matrix A has 2 non-empty tiles, A00 and A02. Find the corresponding vector tile x0 and x2, both of which are the non-empty tiles. Multiply and add the resulting vectors to get y0, the first tile of y. The second row has a non-empty tile A11, which matches the second vector tile x1. According to its index, it is judged that x1 is an empty tile, so no need to calculate. Part 3, tile BFS. TileSpMSpV can accelerate BFS, so I will introduce tile BFS using TileSpMSpV next. Since we only focus on unweighted BFS, we optimize the data structure of the matrix and the vector. First, only non-empty matrix tiles are still stored. Use dense and dense matrix tile in binary mask format instead of sparse matrix tiles. Set to 1 if there is an edge, otherwise set to 0. Then use a number to store a row or column of matrix tile. The size of NT is 16, 32, or 64, corresponding to unsent char, unsent int, unsent long to store. A matrix tile can use 16, 32, or 64 number for storage. We choose the size of NT according to the size of matrix. Next, whether to use row-wise SPMSPV or column-wise SPMSPV. When the input vector is dense, we choose row-wise SPMSPV. Between matrix tiles, will be stored by row, and within matrix tiles will also be stored by row. When the input vector is sparse, we choose column-wise SPMSPV. Columns are stored between matrix tiles, and columns are also stored within matrix tiles. We will store both formats, and when using indirect graphs, they are the same, just save it once. Finally, regarding the storage of sparse vector, we also store the dense vectors in binary mask format. BFS has two vectors. One is input vector x, and the other is the mask vector m, marking whether the vertex has been visited. Since the density of matrix and vector will greatly affect the calculation amount of multiplication, it is difficult for a single operation method to maintain high performance according to the sparsity of the input vector and the number of vertex visits. TileBFS divides the processing method into three kernels called push set C, push set R, and pull set C. Both matrix and vectors are bit masks that converts matrix multiplication operation into binary and or hard ring operations. First, the input vector of the first layer of BFS has only one non-zero element, and we choose the push sets C method. According to the non-zero element position of the input vector, several corresponding columns are found, that is the first column of the matrix, and then merge it into Y. Finally, update vector m and x. In the second layer, the input vector is relative dense, and the number of unvisited vertices is large. We choose the push sets R method. By multiplying each row tile of the matrix by corresponding vector tile, the resulting vector A tile is obtained. In the second layer, the number of the unvisited vertices is small, and we choose the pull set C method. First, the input vector is calculated according to the mask vector, and then the corresponding matrix column are founded according to the non-zero element position of the input vector, and then it is merged with the mask vector. If the result vector has non-zero elements, it means that the parent vertex of the unvisited vertex has been visited. Then the vertex can be added to vector m. Finally, after updating x, if x has no non-zero and if the x has no non-zero elements, then BFS ends. Next part, we test the SPMSPV and the BFS algorithm on Aveda GPUs. The dataset was selected from the TileSpMSpV matrix collection. We also select 12 matrices for detailed analysis. This is the performance comparison of TileSpMSpV, TileSpMSpV, Cablas, and TileSpMV, and for vector sparsity on RTX 3090. The super subgraph is the performance and the lower is the speed up. It can be seen that TileSpMSpV has obvious performance advantages. When the vector is dense, the performance is higher than other algorithms, and as the sparsity increased, the performance is higher. Um, the TileSpMSpV can achieve average over 1.8 times up to 7 times, over 17 times or up to 1,000 times, and over 17 times up to 200 times speed up. This is our TileBFS and Guangming G-Switch's BFS algorithm performance comparison on two NVIDIA GPUs. On RTX 3060, the average speed up over Guangming and G-Switch are over 3 and 4 times. On RTX 3090, the average speed up over Guangming and G-Switch are over 2 and 20 times. It can be seen that the scalability of our TileBFS is better than other algorithms. For a more detailed analysis, the figure shows the performance comparison of 12 typical matrices. Our algorithm performs well on matrices with less than empty tiles and dense distribution of non-zero in tiles. The matrix L is an example. For these matrices, we use less memory and increase the parallelism of CUDA kernels. We test the performance of 3 BFS kernels, task incrementally, and in the future, the push set C is K1, push set R is K2, push set C is K3. It can be seen that with the increase of the number of kernels used, the performance improvement is obvious. On this matrix, the highest speed up of over 7 times is achieved. We test the BFS iteration time, and we can see that our algorithm pressures the peak execution time, but there are some involved transitions. This is a comparison of the time with a CSR format matrix is converted to a tiled format, and the execution time is of the BFS. The time for format conversion doesn't exceed a single BFS precision time in most cases. Enterprise is the first BFS algorithm that performs different load balancing for different outer degrees in BFS. The figure shows the performance comparison of TileBFS and Enterprise on RTX 3090, and the average speed up is over 1.3 times, and the max speed up is over 2 times. Part 5. In this paper, we have proposed a tile storage structure for sparse matrix and vectors, and we designed a tiled sparse algorithm called TileSpMSpV and a BFS algorithm called TileBFS. Compared to existing work, our experience shows that the TileSpMSpV and TileBFS bring obvious performance advantages. That's all. Thank you.